So today, we're going to talk about the mathematics of perspective in art. We're going to find out the best place to stand in an art gallery, the modern applications of the medieval Chinese alternative to perspective, and you're going to learn how to make your very own Holbein-inspired perspective illusion. So, it's almost exactly 600 years since Filippo Brunelleschi discovered the mathematical rules that underlie perspective. And if we look at Italian art that was being produced in the few years before that discovery, we get these are beautiful, beautiful pictures, right? So this is by Duccio, and you can see it's a lovely thing to look at. But if you look closely at, say, this throne here that Mary is sitting on, it doesn't look quite right in terms of the perspective. Another image of his here, you can look at the floor, and again, that's even more not quite right. That isn't using correct perspective. Now, these are great artists. Why aren't they using perspective? Why hadn't perspective been discovered sooner? And after the discovery, we get these delightful pictures. This one's by Fra Carnevale, the Annunciation, and you can see, all the perspective is just lovely and harmonious and beautifully, correctly done. This hadn't been discovered earlier, I think partly because there wasn't as much need for it. The style of art in pre-Renaissance Italy was more in the Byzantine style. It is stylized. It's not supposed to be naturalistic in as much as you don't have the figures in realistic settings so much. But when that started to come in and you started to want to put people in rooms, on thrones, then you really need to understand, how am I going to portray this accurately? So here comes Filippo Brunelleschi. He is a many-talented person, architect, sculptor. He designed the dome of Florence Cathedral, so he's shown in this picture with his picture for it. This is a hugely impressive feat of engineering and architectural design and mathematics. It's still the largest brick dome in the world, so that's not too shabby 600 years later. As part of designing it and planning for it, he's believed to be the person who had obtained the first ever patent in the world, and it was for a huge boat called Il Badalone that could carry the vast slabs of marble required to build this magnificent building down the River Arno, and it needed a specially constructed boat. And so he got this patent, and no other new boat designs were allowed on the River Arno for the following 3 years. Actually, don't tell anyone, but the design didn't go too well. They didn't actually even try it out till 6 years later, and it sank. But he invented the rules of linear perspective, so well done to Brunelleschi. One of the rules then, and we can sort of feel intuitively that this is right by looking at a photograph, so obviously something not available to Brunelleschi to do, but if you look at a photograph, you see the parallel lines that are receding into the distance, so not the verticals that are themselves parallel to the picture plane, but the lines that recede into the distance that are parallel look like they're all going to meet and converge on a point. We call that point the vanishing point, and if I've just drawn in some of those lines, that is happening on this photograph. Now, that's not a mathematical proof, but it's sort of convincing evidence, and it's a very good photograph because it draws our eye to this bust that is the subject. So Brunelleschi doesn't have a photo to look at, but he did have a nice demonstration of this that I'll show you in a second. So that's one of the rules, that parallel lines that are moving not within the plane of the picture should converge onto a single point called the vanishing point. Now, of course, if you're trying to draw accurate pictures, and if you're a good artist like Giotto, you can tell that lines that are parallel to each other, like the ones in the ceiling of this picture here, some of which survives, they ought to kind of get closer together as they get further apart. But if you follow the lines of those from this picture, you find they sort of do, but they don't all meet in one point. So this is kind of good artists, a good artist drawing by eye and getting something about right, but clearly that he is not following the rules of perspective there, and they are not yet known. But you can get approximately close by eye, of course. So I want to talk you through this vanishing point idea. Why do parallel lines, which clearly don't meet in real life, I mean, that's almost the definition of parallel, right? Parallel lines don't meet. So why on earth should they meet in a picture, in an image? Well, they don't meet in real life, but if you're looking at a real-life picture, or you're looking at a scene, train tracks going into the distance, they look like they're getting closer and closer, and perhaps they might meet, but where they do meet, we could say they meet at infinity, but of course that's so far away, we can't see it, and it's vanished, right? So hence vanishing point. So why should that be true? Let me explain why it's true. So when you're drawing a picture, of course, what you want to do is you're sort of imagining, there's your eye, E, and you're looking through a window at the view. And you want to replace that window instead with a picture that perfectly renders the view exactly. So what you want to do is say there's a point over there, the ray of light that's coming from the point to your eye will pass through the picture plane somewhere, and that should be where you draw the image of your point, right? So it's just where the line from the point to your eye crosses over the picture plane, that should be the image, and I've called it P dashed. And you can do that with all the other points. There's another one, Q, which has an image Q dashed. Again, it's where the line to your eye crosses the picture plane. And so if you have then lines, say the line PQ, it will have an image line P dash Q dash. Jolly good, jolly good. So far, so good. And underlying this is the problem we're trying to solve is to represent the three-dimensional world. We're going to try and project it onto 2 dimensions. So this is one way of solving that problem. So what about this vanishing point business? Well, let's imagine then we have a bunch of parallel lines somewhere in your picture. So these might be kind of the lines of floorboards receding into the distance or something like this. So those blue lines, they are all parallel to each other, and they are not parallel to the picture plane. So they're not, vertical lines would still remain parallel to each other. But anything that isn't in that plane, we expect to get closer together in our image. So there's a bunch of parallel lines, and I'm going to define a point for you now, which is going to be our vanishing point. And the way we define it is we say, okay, it is the line from our eye parallel to this collection of parallel lines. And that is going to hit the picture plane somewhere, let's call it the point V, where it hits the picture plane. So now, the claim is that any image of any of these lines here, these parallel lines that we're trying to draw, any image line is going to, if we extend it suitably, it's going to hit that vanishing point. So let's check that out. So let's pick one of these lines, PQ. If it works for this generic line, it's going to work for all of them. And we can draw our proposed vanishing point. It's the line from our eye parallel to PQ. So we do that, and it meets the picture plane at V. Now you've got these 2 parallel lines, and in between them, if you sort of drag one to the other, it'll mark out a plane, a flat plane, with these 2 parallel lines. And that plane, slanted plane there, is going to meet our picture plane, and the intersection of 2 planes is a line. And you can just see that line on the screen there. Now on that line, we've got various things happening. Which points lie both on the red plane and on the picture plane? Well, V does. That's how we made V. And P dash, the image of P and the image of Q, also lie on that line, because they are precisely where the line from E to P meets the picture line. So that's on the plane, and so is Q dash. So therefore, what have you got here? You've got this line, and it contains P dash, Q dash, and V. It contains the images of the points, and they all lie together on the line. So if you just extend that line, P dash, Q dash, it has to go through the vanishing point. And that argument is true. We just took any old line, right, in that collection of parallel lines. So we're done. So that's why there is a unique vanishing point. So Brunelleschi was correct. Now, he did not have a photo to show his friends and draw lines on it. What he did was he took a takes no prisoners building here. This is the Baptistery in Florence. It's right next to the cathedral. It is an octagonal building. You could not ask for more straight lines in a building to draw to demonstrate perspective being correct. I've just shown you a couple of, well, just one of the vanishing points there for that facade that's at 45 degrees on this octagonal building. So what Brunelleschi did was he painted a picture of the Baptistery, and he rigged up a little bit of kit. So he took his picture, actually it was a mirror image of the Baptistery, and he made a little hole in it, and what he got people to do was stand precisely at the exact vantage point that he'd done the picture from. And then they would look through a little pinhole through this picture, and there was a mirror that you could gradually slide across in front of your view. And the mirror would then show his picture gradually appearing, and it was sort of covering over the real image that they were looking at, and they were exactly the same. So this is a very compelling demonstration that the rules that he'd devised, the maths all works, but sometimes people like to actually see it working, for real. So that was a very good demonstration. So Brunelleschi made these rules, and he showed them to people, and they caught on instantly. So within 5 years, it was 1421-ish, 1420, that he came up with these rules, as I say, 600 years ago. Within a few years, this is 1427 approximately, this painting by Masaccio, tribute money, it was using perspective, the new rules. So there are some parallel lines here in this picture. You can see them coming down and up from the building, and if you follow them to the end, they all meet up at one point. And of course, because you can now make this kind of decision, where do they meet? Where is the eye pushed to by all of these essentially arrows? It's the most important figure in the painting. That's Jesus there with his disciples. So you can choose then where to put your vanishing point. That's another little trick. So clearly this is someone who knows what the rules are and is applying them cleverly. One other thing that we can see from this picture is another of the rules of perspective, that when you're drawing a group of people, even though, of course, we know that if you're looking at a view, as people are further away, they should appear to get smaller. Big things are close, and small things are further away. All their heads are level. So how can that be if it's all correctly in perspective? Well, the reason all their heads are level is because if you think about what you're trying to do, you're trying to project this three-dimensional thing onto 2 dimensions. You are drawing lines from their eyes to your eye. So if we're all standing on level ground, and if we're all roughly speaking the same height, then all of the eyes are roughly speaking at the same level as our eye, the viewer. So that's why they are all on this horizontal line. So how does that square with the figures should get smaller as they're further away? Well, look at the feet. This guy's close, this guy's a bit further away, his feet are a lot higher up. So that's how that works. So if you want to draw a nice group of figures in perspective, the eye lines of all should be roughly the same. There is a guy bending over in the background, but he's bending over. Now, the rules of perspective were introduced by Brunelleschi, but they were popularized a lot by this chap, Leon Battista Alberti, who wrote a book, importantly in Italian, in the vernacular language. And this meant it wasn't just for the intellectual elite. This was for the people who were actually making the art, making the pictures, della pittura. There was a Latin version as well, but it was important that this version was in Italian. And this spread the word even further. And he was a very interesting guy. He wrote a lot about various different fields of study, architecture, painting, and he was very up on the link between mathematics and these other subjects. Mathematics is important for everything. He says, in this commentary which he dedicated to Brunelleschi, I'm going to tell you first the things that come from mathematics. They're the best things, of course. One thing Alberti included in his book, and this is a picture from his book, is how to deal with the problem of a tiled floor. So we've already seen, we know that the parallel lines on a floor, imagine a square tiles on the floor, the parallel lines that are receding back, we know what to do with those, they have a vanishing point. But if you've got square tiles, then the horizontal edges of those tiles are parallel to the picture. So they remain parallel to each other, they don't go off to a vanishing point. The problem is that, as we all know, if we look at a tiled floor, the tiles towards the back appear to be getting, well, they don't appear to be getting thinner, but the gaps between them are getting smaller. Otherwise, it looks wrong. So you have to leave smaller and smaller gaps between these horizontal lines, but how wide should the gaps be? That is difficult to know, because we don't have a vanishing point for those. However, clever trick, which Alberti is describing in this diagram, the diagonals of these square tiles are not parallel to the picture plane, so all those parallel diagonals do have a vanishing point. So here's the way to draw your tiled floor, and you can all go home and do this tonight. You get your lines from front to back, those edges, you can just equally space some lines and make your vanishing point, and that's done. Then you draw the first horizontal line, and that's going to be your first square tile. And depending on how quickly receding into the distance and the angles and everything, you can basically choose and decree that to be square, and then everything else has to match up with that first tile. So how do you do that? Well, you draw in all the diagonals. I mean, you can draw them in pencil and then rub them out later. You draw them all in. They would all go and meet at a vanishing point. So you find that vanishing point, and then you can draw in all these other diagonals based on the first row of tiles. And then, what have you got? You've got a load of diagonal lines, and you've got a load of front-to-back edges. And every time an edge meets a diagonal, what's that? It's a corner. So you acquire for yourself, just from that first horizontal line, you acquire for yourself a bunch more corners on the rows above. So then you can start to draw in the other horizontal rows. And every new row you create allows you to draw in a few more diagonals, and then you can draw a few more rows, and over and over and over until you construct your whole floor. So this was one of the diagrams that Alberti drew and explained how to do this process. So we can draw a tiled floor. Marvellous. This is it's sort of an epidemic of tiled floors in Renaissance Italian art, by the way. Like, if you look at a picture done in 1400, probably not a tiled floor. If you look at it in 1436, it's like 90% chance of a tiled floor. Don't quote me on that. 74.6% of statistics are made up on the spot. So we've seen so far in all of our pictures that there's sort of one clear vanishing point, though there may be others hiding around in diagonals and things. I just want to show you kind of 3 different ways of drawing a cube using perspective that are referred to as 1-point perspective, 2-point perspective, 3-point perspective, even though all of these pictures really have many vanishing points in them if you draw in diagonals and things like that. But these are the obvious ones. So on the top left there, you've got a cube where it's sort of square on, literally. So you've got the verticals and the horizontals are parallel to the picture. And so they stay parallel, they don't have a vanishing point. But the receding lines do. So that's 1-point perspective. The one in the bottom middle, it's sort of like, imagine a building on a street corner. The verticals are still verticals. They are parallel with the picture plane. But you've got 2 receding to the left and to the right. And so that would be 2-point perspective, so-called, because there's 2 obvious vanishing points. And the one on the top right, in that you might have a sort of bird's eye view of a building or something like that. It has 3 vanishing points that are sort of clear to us. As I've said, in all of these, there are many more that you could find, but these are perhaps the most obvious ones. So if you're an artist, you know how now to do your lovely perspective drawings. For us who are viewers of art, can this help us to appreciate art more? Well, of course, it's always nice to know how things were done, but on a more practical level, if you're in an art gallery, if we understand these rules, we can use them to try and work out where's the best place to stand to view a picture. So, starting with this, this is not a great work of art. This is just that cube I had a moment ago that has 3-point perspective. So it's got these 3 vanishing points, and these are associated to the receding lines off to your left, and the ones off to the right. The ones sort of to the left have this vanishing point U, the ones to the right have the vanishing point V, and the ones that are going downwards have the vanishing point W. I want to convince you first, how do we know where to stand to see this? I want to convince you first that there is a unique answer to this. There's only one possible place we can stand to see this in its correct perspective. And then I'll show you how to actually find that place. So we've got these 3 vanishing points. Now, remember how we defined our vanishing points. It's you stand where your eye is when you're making the picture, the line from your eye that's parallel to the appropriate collection of parallel lines, right, that hits the canvas at what we call the vanishing point. So that point U, that's associated to these parallel lines zooming off to the left. So from our eye, the line to U is parallel to all of those, and the line to V is parallel to all the lines zooming off to the right, and the line to W is parallel to all the lines going downwards. So at the point, a correct vantage point, you've got these 3 lines coming out, and they are having exactly the same geometrical relationship to each other as what happens at the corner of the cube, right? They are all perpendicular to each other, to the left, to the right, they're at right angles. In the real world, let's say, this is obviously this is the perspective image, but in reality with a cube, these are all at right angles, and so those lines to the vanishing points have to also be at right angles to each other, because that's how we define them. So what you've got, I'm just going to show you looking down on this image, just at U and V, and then the putative I, that's supposed to be the ideal vantage point. What you've got, so there's my U and my V in the picture plane, there's my I, E, and if we draw a triangle in now, so the line from U to V, the line from E to U and the line from E to V, those have to be at right angles, because the original sets of parallel lines were perpendicular. So we've got a right-angled triangle here. Now, here comes the science bit. Think back to when you studied circle theorems at school. Do you remember a phrase coming back into your mind? Angles in a semicircle are 90 degrees, or there's a right angle in a semicircle. Just flick back through the memory. The fact that this is a right angle here means the point E, the I, the ideal vantage point, lies on a semicircle with diameter UV. So that's useful information. Of course, we're living in 3 dimensions. We don't know which semicircle, because it could be, at any kind of orientation. So what we really know is that the ideal vantage point lies on the sphere with diameter UV. It's somewhere on that sphere. But we've got another vantage point, another vanishing point, W. And we could do exactly the same trick with the pair U and W. The lines from them to the vantage point, to the eye, have to be at right angles. So this point E has to lie on the sphere with diameter UW and on the sphere with diameter VW. So this ideal vantage point, it's not a great, I've tried to make it as visible as possible, but it has to lie at the intersection of 3 spheres. Now, 3 spheres that intersect do so at precisely 2 antipodal points, North Pole, South Pole, right? So this is one solution, and this is another one. Now, I said it was a unique thing. There's only one vantage point. Yeah, that's because this other point is on the opposite side of the picture. It's behind the picture inside the wall, right? So we can't stand there. So there really is only one answer. There's only one place to see a perspective drawing from in exactly the right place. I mean, if you stand near it, you'll get a pretty good idea. But there's one unique vantage point. So, okay, fine. You've shown us the 3 intersecting spheres, Sarah. Where do I stand in the art gallery? Okay, here you are in the art gallery. You're looking at an old master. Where am I going to stand to get the perfect perspective view of this? Well, let's remove the extraneous detail from this, i.e. everything that makes it amazing, and have a slightly simpler thing to look at, my amazing empty room perspective drawing, which I'm sure will be on display in the National Gallery before too long. So here we are looking at this. Where do we stand to get the best view of this amazing work of art? Well, we can use what we know about vanishing points. So do not go up in an art gallery with a big ruler and make a big red blob on a Vermeer. Don't say Sarah Hart told me I could. I didn't. But you can maybe do this at home first or something, or do it by eye. You can work out where the vanishing point is for the lines of these tiles that go, the edges that go front to back, and for the diagonals, one set of diagonals. And then we can do a bit of thinking. So this floor that's in the picture should be, if we're looking at it properly, it should look like completely flat and level and horizontal like a floor. And we're standing on a floor, flat and horizontal. So any lines in that floor that's in the painting, they are all lying within that plane. And remember, the lines from the perfect vantage point from our eye to the vanishing points have got to be parallel to all of those lines. So they are all going to lie, they're going to be parallel, but at the level of our eye. So if we find that vanishing point, she might need to stand on a little stool or something, because her eye needs to be level with that vanishing point to get the perfect view. And then, so that's all right. So the eye has to be along a line that's coming directly out of the picture, somewhere from that vanishing point, somewhere along that line. So that's a start, but how far along that line is the question. Well, there's a bit more geometry we can do. If you think about these diagonals and the straight lines going to the back, they form a nice right-angled triangle. and it has 45-degree angles. And so in particular, the two sides, this side and this side, are the same length. It's an isosceles triangle. So now think about what's happening in the relationship between the eye being in its perfect place and the two vanishing points there. We know that the line from the eye to the vanishing point of the front to back lines and the line from the eye to the diagonal vanishing point, they should be at the same angle that those lines are really at, because they're supposed to be parallel to those original lines. So they should be at a 45-degree angle. And you get the line that's coming out of the picture and the line within the picture between the two vanishing points, those are at right angles. So you precisely get another of these 45-degree right-angled triangles. It's isosceles again. It looks a bit wonky because this is my perspective drawing of how to do perspective drawing. So this green triangle up here also has to be an isosceles triangle. In other words, the distance from your eye to that vanishing point up here should equal the distance between the two vanishing points on the picture. So that's how you can work out where to stand. You stand directly in front of the vanishing point for the straight lines and at the same distance back from the canvas as the distance between these two vanishing points. So that's where you stand in an art gallery. Okay, so that's kind of one piece of advice. Now, perspective was obviously very much employed and still is in art, but it has a modern-day application that Brunelleschi 600 years ago was unlikely to have predicted, I don't know for sure. And that's in films. So this is a still from a video that's up on YouTube. You can go and look at it. I've put the link in the transcript. But it's by the company Framestore, who do visual effects for the Paddington films, which are glorious things to behold. And, you know, this is computer-generated imagery. What they do is they sort of mix together real-life video footage, and then they add in extra bits that are difficult to produce in real life, like a talking bear that eats marmalade sandwiches. So this scene that they're showing here, I've just got a couple of stills from it, they've taken this video footage of, you know, a road in the English countryside, which of course you can see perspective happening, but they have to understand the rules of perspective in order to overlay onto it this fast-moving train with lovely train tracks. Look at all those beautiful parallel lines receding into the distance. It's a very exciting chase on the top of the train between poor old Paddington and the dastardly villain Phoenix Buchanan, if I remember his name rightly, who is played with considerable relish by Hugh Grant. So, yeah, worth watching just for that. But all of this requires knowing perspective and getting it exactly right. Of course, Paddington himself is also has to be in perspective, but it is harder to see underneath all that fur the correct mathematics going on, but it's there. So we see it in modern films, and it's absolutely vital for that to get the effects correct. Once you know the rules of perspective, if we go back to art, you can start using them in a way I've hinted at already, which is to kind of make a point or to add to the symbolism of your picture. So we saw earlier that the vanishing points of that picture by Masaccio, Tribute Money, they all kind of joined. The vanishing point was the face of Jesus. He's the most important guy in the picture. This picture, which is by Veneziano, another Annunciation, we saw an Annunciation earlier by Fra Carnevale, you can see this beautiful perspective. It's all very good. So this is the angel Gabriel is announcing to Mary that she is going to conceive a child miraculously, and that child will be the Son of God. So where do you put your perspective? Where do you put your vanishing point in that picture? You might think, well, it should be one of the two figures, maybe. But if you look at where it is, the vanishing point there is at this sort of innocuous-looking locked gate that keeps people out of the garden, right? So there's a locked gate, and this is a symbol. This is symbolic of Mary's virginity, right? So that's an extra layer of symbolism to add to the, emphasis of what's going on in this story. That's a conscious decision. So Veneziano obviously could wield the rules of perspective. So if you look at this other picture by him, Saint Zenobius Performs a Miracle, given that we know he knew the rules of perspective, we've got this other, almost contemporaneous picture by him using the rules of perspective to impart symbolism. If we look at this picture, so what's this showing? It's showing an absolutely distraught, anguished, confused, distressed, grieving mother whose child has died, and St. Zenobis is praying for the child to be restored to life. How do you use perspective then to emphasize what's going on in this picture? Well, you know the rules of perspective say everything meets at a vanishing point, but they don't. They don't quite meet. And this gives us a sort of air of slight disconcertedness, I suppose. It surely must be done on purpose to emphasize the action of the scene, this confusion and grief of the mother. So you can use it, and you can deliberately not get it right if you want to send that message. You can also trick people. So you can use perspective effects to make people think what they're seeing is not what is really there. So this is called a false perspective gallery. It's in Rome. And here, it looks very, very much longer than it really is. It looks like it's about 20 meters long. But it's actually been cleverly designed to look longer, and it's really only 8 meters long, I think, because they've used the rules of perspective. These aren't really parallel lines, but you just assume they are. Much later, we get people like Hogarth, famous satire and false perspective. This was at the beginning. This is the frontispiece of a booklet on perspective that his friend Joshua Kirby had written, and I've just sort of enlarged the writing that's at the bottom of this. Whoever makes a design without the knowledge of perspective will be liable to such absurdities as are shown in this frontispiece. And if we look, let's make sure everyone sort of at the back can see, but there are various absurdities. Indeed, in this picture, it's got an inn in the foreground, and then various things happening in the background that doesn't quite look right. Locally, it all looks okay. Like if you look at any little bit, it looks okay. But then if you look at the whole, impossible things start to happen. And perhaps the most obvious of these is that if you look at the top, there's someone hanging out of the window of the inn with a candle, and she's lighting the pipe of the chap who's on the far distant hill, who should be completely unable to actually do this. But, it all looks right, just it doesn't work globally. This is the kind of trick you can do if you're a master of perspective. And of course, more recently, we have the work of artists like Escher, who have got kind of waterfalls whose water from them feeds into themselves, and stairs that go forever upwards, and things like this that again trick us by making us believe in the perspective locally that then falls down globally. Now, you could very sensibly ask, what's going on elsewhere? So why we sort of saw why there might be an impetus for perspective to be discovered in Renaissance Italy when people wanted to turn to a more naturalistic style of painting. What was happening elsewhere? Was this discovered elsewhere? If not, why not? And usually with these kind of things, and it's true here, it's not because there was there was a particular genius happening in Renaissance Italy, but it's not that there weren't geniuses elsewhere in the world, right? It's because different forms of art have different challenges that require different solutions. So there's some evidence that there was at least partial knowledge of the rules of perspective in ancient Greek and Roman art. What knowledge there was, though, was lost and had to be rediscovered. We'll never know if they knew all the rules or not. They certainly weren't written down. But if you look at ancient Egyptian art, it's a solution to a problem that isn't there, because the art is not supposed to be naturalistic. It's hierarchical. It represents things not in a realistic way. I mean, just look at the way the bodies are. We have this convention that the torsos are all front-facing, the legs are always sideways, side profiles of all the heads. And big things does not mean they're close, and far away things are not small. Bigness, size, is to do with how important you are. So the gods are the biggest things in the picture. Then it'll be the nobles. And then, right at the bottom of the pile, the slaves will be painted very small. That does not mean that they are far away. Okay, so this symbolic almost painting, there's no need to develop perspective, because that's not what you're trying to achieve. And here this is a painting in a tomb. This is not kind of still life with fishes. Here's all the stuff we've sent you to the afterlife with, and then you have to be able to see it all. So that's not realism. Is not what the aim is here. If you move forward in time, if you look at what's happening in Chinese and in Japanese art about the time of the Renaissance in Italy, Why isn't the perspective discovered there? Well, because it would be totally irrelevant to the art forms that were there. Reason? If you're a 15th century Chinese painter, you are probably painting a very long painting along a scroll. That tells a story as you move along the picture. Just have a piece of water. There's one to look at while I have a sip of water. So this is actually a picture made in 1820-ish by the Japanese artist Hiroshige, and it's a picture of a kabuki theatre. You can see that what is happening here is not our linear perspective that we've been talking about, and there's a good reason for that. If you're painting along a scroll, some of these scrolls could be 10 meters or more, where's the vantage point? There is no vantage point. Your eye is constantly moving along the design as it tells a story. So perspective just isn't the solution here. It's not going to work. It's not an appropriate thing. If you did try to have a fixed vantage point, then the ends would be hopelessly distorted and you're not going to be able to see. So you want a solution where your eye can move along the picture and not have a fixed vantage point, and this is the solution that was developed, very ingenious. In English we call it axonometric projection. And you can see what happens here is parallel lines stay parallel. The angles between them, so this would be a right angle in real life, and it's portrayed as not a right angle, but that's the concession that's made. And the distances or the sizes of figures, there's no diminution as you move into the background, and things don't grow bigger as they go into the foreground. They're the same size, so it gives you this sort of panoramic viewpoint. And that is really, really useful, actually, in some modern-day applications. It's a very ingenious solution to the question of how we portray something. So it has been exploited by modern artists, such as Roger Brown, for example, and some other Chicago artists were exploring these ideas in the 70s, 80s. And you can see this. Here are these two parallel roads. They are not getting closer together as you recede into the distance. It gives this slight air of unreality, but it also is sort of a democratic way of showing things. The figures aren't getting smaller the further away they are. Everyone's got their own egalitarian perspective in these kind of pictures. You can move around and there's no single vantage point. There's important technical applications too, though. In technical drawings, this is a patent application from the 1880s, I think. So this is done in axonometric projection. What's useful here is that we've said, there's no diminution in size as you go forwards and backwards along axes. The scaling factor is constant. So axonometric actually comes from words meaning measurement by the axes. You could actually take measurements from this picture. Even though it's showing a three-dimensional object, you can take measurements from it, and that's important, obviously, with a technical drawing or an architectural drawing. There are more symmetrical versions of axonometric projection. So isometric projection, which is a word we may be slightly more familiar with, that means it's the same scaling factor along each axis. So that's the easiest one to use because you just need to know what the scaling factor is. Then you can take measurements and retrieve what you need to make this design. The most symmetrical form of isometric projection is where the angles between the axes are all the same, 120 degrees. And you may have seen or used isometric drawing paper, which allows you to make 3D-looking drawings, diagrams, like this not very good one I've done here just to show you. So this is kind of a lattice of equilateral triangles. It allows you to get those 120-degree angles between the three axes. And so this old technology or idea of axonometric projection has got very modern applications. And there's one that, perhaps is really quite unexpected, given this is developed to solve the problem of huge, long painted scrolls. We don't look at huge, long painted scrolls depicting invented worlds anymore, but we do look at some invented worlds. And if anyone wastes time playing phone games, where you have worlds and you build them and you add buildings in and you move trees around and things like that, don't waste time, spends time relaxing. Then you'll be familiar with things like this, right? So this one is called Big Farm, but they're all very similar. You build a world and you can move around in the world, and it's really, really useful to be able to have not real perspective, but this axonometric perspective where everything stays the same size, and it doesn't matter from which place you're looking at it, because sometimes you want to move things around. You go, can I build a big barn in that space? And you check, and you can, and you know you can because you see it here, and it's going to stay the same size when it moves over there. So moving around in these imagined worlds is something that modern games do all the time. And so this is an absolutely vital bit of the technology that enables us to do this, and it comes from these medieval scrolls and that solution there. So as I say, that was the right solution for that art form, and linear perspective was the right solution for the Italian Renaissance. So we're going to, in a little while, we're going to talk about the sort of strange perspective illusions of the sort that Holbein created. But just before we do, I want to mention that the mathematics we've seen so far, it's got some geometry in it, circles, squares, triangles, but it's mathematics that was understood, by 600 year ago people. However, this has had a huge effect on modern mathematics, far beyond what you might expect from looking at what we've talked about so far. And the reason is because it kind of put a seed in people's minds with this crucial observation that these parallel lines we're talking about meet at infinity. And so that's why when we have the image of them, they're meeting at the vanishing point. And at some point, it sort of became, and it gives a sort of respectability to infinity. All these parallel lines, a collection of parallel lines, they will all have a point at infinity where they meet. And sort of a step you can then take once you're comfortable with that idea is to say, well, let's sort of incorporate this point at infinity into our geometry. So we've got all the sort of standard points in space. We'll just throw in all these points at infinity, one for each collection of parallel lines. And going down that route, you think, that's a bit weird, why do that? It gives you this very nice duality and simplicity to some of the rules of geometry. So we all know, mathematicians like universal rules, right? We all know the rule that says any pair of lines meet in exactly one point. Oh, except if they're parallel. We don't like except if. We like everything to be true, we like it a universal rule. So with this point at infinity idea, you can do that. Any pair of lines meet in exactly one point. And the ones that we call parallel, the meeting point is the point at infinity. Okay, so that's quite nice. You can just say that is true. And you can also go in reverse. You can say that any pair of points define precisely one line. So if these points are in sort of normal space, you just draw the line between them. There's exactly one of those, job done. If one of the points is one of these points at infinity that you've just added into the mix, then what do you do? Well, it's basically the parallel postulate, because that point at infinity, that's connected to a collection of parallel lines. That's how we define these points at infinity. So it is the point where all these lines that are parallel to each other meet. Here's your other point over here. Through any point, there is exactly one line parallel to your favorite line over here that passes through that point. So if you have a point at infinity, that gives you a direction for the parallel lines. And then there's exactly one of those that goes through your favorite point over here. So any 2 points do define a unique line. So with this idea, you've got this nice, it sort of simplifies things a bit. But it also gives you a really elegant way to do some kinds of mathematics, some kinds of geometry. And I just want to give you 1 minute about conic sections, which these are. You may or may not recognize them. Slight advert for later in the year. I'm doing a talk all about conic sections, so you should definitely sign up for that and come to that. But in the meantime, on the left you've got an ellipse, in the middle you've got a parabola, on the right you've got a hyperbola. Now these three curves are not randomly joined together, linked and called conic sections. They are curves you get by slicing through a cone. So if you take a sort of shallow slice, you get an ellipse. And if you go a bit further, you start to get a parabola, and then if you go even further still and cut into sort of the top half of the cone, you get hyperbolas. So these curves are linked to cones, but they don't seem very similar to each other. It's sort of weird. They're connected somehow because you can make them by slicing through something, but they don't seem to have much in common. However, with this amazing projective geometry idea of adding in points at infinity, you can treat these in a very elegant way and analyze them all in one go. And the reason is that, say, look at this guy, this is a hyperbola. It's got two branches to it, and the ends of each branch zoom off to infinity. But they zoom off in two ways. Two of the ends zoom off and become sort of parallel to the vertical line. So they'll join up, they'll meet up at the point in infinity corresponding to vertical lines. Meanwhile, the other two branches, the other two ends of the branches, zoom off to horizontal infinity. So they'll meet at a different point in infinity. So this guy meets infinity twice. What does the parabola do? Its ends zoom off to infinity and they become closer and closer to vertical. So they join up at infinity at one point, the point where vertical lines meet. So what's that got to do with anything? Well, if you take an ellipse here, we know that any line you can draw cuts an ellipse either not at all, or exactly once if it's just kind of a tangent to it, or exactly twice. These three curves, I claim, they're all ellipses really. They're all ellipses really, but the true ellipse meets the line at infinity made up of all those points in 0 points. The parabola meets the line at infinity in exactly 1 point, the vertical vanishing point, and the hyperbola is an ellipse that meets the line at infinity in exactly 2 places. And you can actually, it sounds a bit sort of pie in the sky, but you can actually do this kind of analysis and understand all of these curves as just variations of the same curve that just meet infinity in a different number of places. So that's super, super cool. Study geometry, it's marvelous. To finish, though, in the 5-ish minutes we have, before I'd like to have some time for questions, I want to talk about pictures like this. So anamorphic perspective. This is where you get perspective used in unexpected ways. So it's still perspective as we've talked about it, linear perspective, but this picture here, oh gosh, I happen to be standing almost exactly the right place to see this properly, but you guys aren't. So let me show you. If you look at this from the right vantage point, this funny blob at the bottom of Holbein's picture, this is what you get. Right, a skull, sort of memento mori, remember that you too are mortal. There it is. So it's a sort of hidden thing to show people. There were a few of these around that sort of time. So this very elongated picture, it's hard to see what it is. But again, if you look at it from the far right-hand side, you find that it's a picture, if my clicker will work. Yes, it's a picture of Edward VI. But you have to look at it from the right angle. Other kinds that we haven't really talked about perspective or pictures you can make by reflecting in mirrors, but you can hide pictures with this kind of trick perspective, or anamorphic it's called, making things anew, that's the root of that word. If there's a picture that perhaps it might be dangerous for you to have in your house, for example, at certain times in history, you may not have wanted to be caught with a picture of Bonnie Prince Charlie, the pretender to the throne, in your house, then what you do is you make a picture that can only be seen correctly when you reflect it in a cylindrical mirror, and then if someone comes knocking on the door, quick, put the cylindrical mirror somewhere else, and what is left, it just looks like a tray with a smear of paint on it. So you can hide your treasonous portraits of people you think should be king in this way. More recently, much more recently, in the current era, we see anamorphic perspective, which really is, it's normal perspective but unexpectedly done, in things like sports advertising, where there's a picture that's painted directly onto the pitch, and it's done in such a way it looks totally wrong from pitch level, but it's meant for the TV cameras. If you're at the correct vantage point, which is the camera, then it appears to be in exactly the right dimensions, and it appears upright, even though, of course, it isn't, because we can't impede the action on the pitch. A good place to see this is in cricket matches, because then you can see at the very top of the pitch that there are 2 cameras, you see, because in cricket, as you probably know, at the end of each over, you have to change the end from which you bowl from. So there has to be a camera at this end, and then one at the other end of the pitch for when they change the direction of bowling. So we can see we're at the point of the camera at the bottom. We can see these 2 adverts all nicely rendered, just perfect for us in the right perspective for our view. But at the back of the picture, you can see the adverts that are intended to be seen correctly by the other camera, and of course they look completely distorted. Now, artists who produce work that is meant to be site-specific, that only exists, in a particular place, have exploited this anamorphic perspective to produce really compelling and really curious pictures. So these 3 pictures, but just look at the top one for the moment. This is by the French artist Felice Farini. Those 9 dancing triangles, they're called, are viewed from the correct vantage point. It looks just like, I've got a picture and just put on top of it, superimpose some pictures of triangles. It can't be real. I mean, it just looks so incongruous. But actually, the pictures below show that same room, but not from the correct vantage point. And you see these kind of blobs of red paint, and it doesn't look like anything. And then it's magic. You stand in the right place, and you see these triangles sort of leap out in front of you. So that's a very clever bit of a trick to pull off. This one. So go and look up this guy, Bruspup, on YouTube, because he makes these amazing. Actually, I don't know if it's a he. They make amazing anamorphic illusions, which I'll put a link in the transcript. So this, for example, just looks like a Rubik's Cube on a table until the hand of the creator comes in and rotates a piece of paper. And it's just a flat piece of paper, just cleverly done with the rules of perspective. So I want to show you in 2 minutes how you can make a picture that is like one of those Holbein stretchy out skulls. So what's happening in these kind of pictures is, you imagine you've got a design, I'm going to say for simplicity a square design, that you want to put onto a picture. This is the picture plane, like usual, and you want the viewing point to be very far over to the right-hand side so that someone looking at it straight on is not going to see the distorted picture. So you'll take your square design, and this will be the projection of it, or the perspective image of it is going to be sort of stretched out, and the square will look a bit like a trapezium, I guess, stretched out like that. And you want to stand very, very close. You want to only see it correctly from very close to the picture itself, to the picture plane. So I've made one or two assumptions just to make it a bit easier to produce for us. So one is, all of the things that are happening that we're trying to represent in our picture are happening on this kind of horizontal plane at the top. And so all the vanishing points will also, they'll be at the ends of lines from your eye that are parallel to that horizontal plane. So where does the horizontal plane meet this plane? Well, it meets it in a vertical line. And then how close you stand to the picture determines, where the vanishing points are going to be. So I've made an assumption. So here is the distorted square. There's the vanishing point of all the horizontal lines in the square, top edge, bottom edge, middle. And I've assumed that the eye is going to be just at that level, so it's nice and symmetrical. And the other assumption I've made is that we're standing at the correct distance from the picture so that the vanishing points of diagonal lines are going to be these, I've called them C and D, they're the diagonal lines from top left to bottom right, from bottom left to top right. I have assumed that the vertical line they lie on, that the distances there make this into just a rectangle. A, B, C, D is a rectangle. Okay, that makes the algebra pleasing. So I divide this rectangle in half here, and so this Z is like the middle of the big rectangle. And we want to find out how we're going to distort our square. In other words, we stretch it a bit, and we have to squash the right-hand side. How long is this line X, Y? Where is it? Similar triangles come to the rescue. The two red triangles are similar. You've got these vertically opposite angles, and you've got the alternating angles, or Z angles, some people call them. So the angle at A is equal to the angle at V. The angle at B is equal to the angle at D. So these are similar triangles. And one is twice as big as the other. So this small red one is half the height of the big red one. So the big red triangle is double the little one, which means that this point X is twice as far from the left as it is from the right. So it's 2/3 of the way along, 2-to-1 ratio. And you can do a similar thing with the gold triangles. They're similar triangles as well, but the bottom one, it's half the width of the top. So this distance to X from the top is twice the distance from X to the midpoint of our big rectangle. So putting all that together, and take a symmetrical argument on the other side for that point Y, what you end up with is that this square should be distorted in this way. It's got whatever height it is on the left, it'll be a third that height on the right. And actually, we can lose the rectangle. That was only for construction. This is the shape you need to make. So there are photo editing programs that you can get either free online or you can pay for them if you like. And all you need to do is take your square image, stretch it as far as you like. We didn't need to know what the width of the rectangle was. It doesn't come out in the final calculation, so that's cool. You just stretch it as far as you like and then squish the right-hand side down so that it's a third of the height of the whole. And I've put one of these in the transcript for you to play with, but I made one, and you can, get it from transcript. This is a mysterious person who is very relevant to the history of this college. And I just want to show you, I could just show you the original picture, but that wouldn't prove this works. I made a very bad video of me, cut it out, stuck it on my wall, and tried to get the right vantage point. And I don't know if you can see this happening, but this figure should appear. Right? And of course, it's Thomas Gresham. So on that note, I will finish. I hope I've given you, sorry for this, a new perspective on perspective. Thank you.
Question, are there any examples of cave art with perspective?
I never like to say a firm no, but I'm not aware of any. I think perhaps cave art is very symbolic, you know. Here's the saber-toothed tiger, here's some people. I don't think, I'm happy to be corrected, but I believe not.
And do these principles, does this apply to military camouflage schemes, for example, ship dazzle patterns?
I'm going to say yes. My feeling is that, if you're trying to create something that will fool an observer, you've got to get your perspective right. So I'm sure you need to deploy some of those techniques. The thing with, I'm not sure exactly what ship dazzle schemes are, to be fair, but one issue might be you've got to be careful if you're using linear perspective, where's the vantage point? So there are kind of trick rooms, for example, that you can make. They're called Ames rooms, where there's a very compelling illusion that the room is properly in perspective, and you can. These were used actually, in the filming of the Lord of the Rings films, where you have hobbits that are small and wizards that are big in the same room, and they created these kind of trick perspective rooms to make those people look very much different in size in what looked like a normal room. So maybe there are tricks like that can be used in those contexts, but of course it requires knowing what the vantage point is going to be.
Back to the Masaccio slide, please.
Yes.
Where the lines were coming from on that one.
Yeah, so I don't know how clear how visible it is from the audience. There were some. You can have a look through. There was a building. There we go. Yeah. So there is a building. Quite. The resolution isn't perfect, but there are lines from the floor of the building, the tiles of the building, another one here, and then at the higher up level, you can see where the second floor of the building is that there are some lines there coming down. And so if I just put those back on, can you see now, like from the corners of the building, that's where they're coming from. So there are some straight lines in the picture. They come from the corners because the other lines that come off from them, they're horizontal lines. So looking at the building straight on, you've got horizontal lines, and then it goes back. So the horizontal lines are not parallel to those ones that I've drawn, so they wouldn't have a vanishing point. It's only collections of lines that are all parallel to each other that have a single shared vanishing point. So we could draw in, if there might be other lines, again, they can't be parallel to the whole picture, otherwise they stay. So the horizontal lines would not have a vanishing point, but it's only the ones, therefore, that are receding into the distance that I've been able to draw a vanishing point on for this picture.
I presume when they started this painting with knowledge, all the tiles were parallel to the plane of the picture. How long did it take before they got the rules right so they go an arbitrary tiled floor?
Yeah, so it took a while, and I'm thinking kind of the zenith of this might have been the old masters and the paintings in the Netherlands that came a little bit later, a century and a half later or so, that are just absolutely amazing. I'm thinking of, there's one picture of a cathedral. It's got these vertical columns and it's got a square tiled floor, and the effect is absolutely amazing, but it's not straight on. So there are these diagonal lines. So I would say And I'm not an art historian, but I think it took maybe 100 years for that to become sort of a commonplace thing. And initially people were like, yay, tiled floors, and you just get a lot of tiled floors. but it does move on from that. And of course, in modern times you get, the building at the corner of a street is a very common trope after a while as well. Yeah.
Would the Channel 4 TV logo graphics application be an example of some of the points you've been making? Have you seen this one where there are bits of the 4 that move around, and then it becomes a 4 from a certain perspective?
Yes, absolutely. And I'm thinking of something we sometimes drive past on the North Circular. There's a kind of sculpture outside of one of the shopping centres that from a certain exact angle looks exactly like a football, and then when you drive past it, the illusion is completely shattered. Or a Penrose triangle, if you've seen those, the actual sculptures of them. They look, of course, they can't exist in real life, but they look real from a certain angle. So absolutely, those kind of things certainly require the understanding of perspective.
Okay, well, I think we're going to have to draw it to a close there. Thank you so much, Professor Hart.